Line integrals part 2. Let C be a smooth, oriented curve parameterized by arc length. Recall that at every point of C, the unit tangent vector t points in the forward or positive direction of the curve. Let F be a vector field that is continuous on the curve. Now suppose we would like to add up the components of F in the direction of t at each point of the curve. Well, let's recall that the components of F in the direction of t is the magnitude of F times the cosine of theta, where theta is the angle between F and t. Since the magnitude of t is equal to 1, this is equivalent to the dot product. So to add up the components of F in the direction of t at each point on the curve, we integrate the dot product over the curve. If C is parameterized by t, then we use identities to rewrite the integrand. So if C is parameterized by t, the line integral can be calculated this way. Let's evaluate the line integral of F on the quarter circle from P to Q. We will start by parameterizing the quarter circle of radius 1 centered at the origin. Sine t cosine t parameterizes the quarter circle oriented clockwise from P to Q. Find the vector field F on the quarter circle. Now that we have written F on the quarter circle in terms of the parameter t, we are ready to find the dot product. We find r prime, and then we find the dot product of F and r prime. After we find the dot product, we use identities to simplify the expression. And we are now ready to integrate. Since it's the quarter circle, we integrate from 0 to pi over 2, and we get that the line integral is equal to -1/2. Let's evaluate the line integral on the quarter circle -C1. So now we're going counterclockwise. This is the same field and same quarter circle as before, but we are now oriented in a counterclockwise direction. And the question is, how will that affect our answer? So we get the orientation for -C1. And then we describe F in terms of the new parameterization, and then find F dot r prime. So F in terms of the new parameterization, and then r prime and F dot r prime. Again, we use identities to simplify the expression, and once we do that, we are ready to integrate. On the quarter circle -C1, the sum of the components of F in the direction of the curve is +1/2, which illustrates the fact that reversing the curve orientation reverses the sign of the line integral of a vector field. And this will always be true. Reverse the direction, you reverse the sign. Let's evaluate the line integral of F on the path C2 from P to Q via 2 line segments through the origin. So this time we're going from P to Q like we did in our very first example, but instead of using the quarter circle, we're using 2 line segments. We need 2 separate parameterizations, one for each line segment. Then we need to define F for each line segment. Then we find the dot product and integrate. The line integral of f from P to Q via the quarter circle and the line integral from f from P to Q via two line segments is equal. This leads to the question, for what vector fields are the values of a line integral independent of path? This question will be discussed in the section on conservative vector fields. A common application of line integrals using the tangential component is computing the work done in moving an object in a force field such as a gravitational or electrical field. The direction of motion at each point is given by the unit tangent vector t. The component of the force field F in the direction of motion is the dot product of F and t. Summing the contributions to the work at each point of the curve is a line integral. F describes the force of attraction of an inverse square force field. Gravitational and electrical forces between point masses and point charges obey inverse square laws. Find the work done in moving an object in the force field along the line segment from P to Q. This will be our strategy in calculating the line integral. Find the parameterization from P to Q. Find R prime. Find F as described on the curve. Describing F in terms of the parameterization, and then simplifying the expression. Now that we have the vector field written in terms of the parameterization, we are ready to find the dot product. Find F dot R prime and simplify it. And then we're ready to integrate. Integrating, we get this expression. If the object is in an inverse square force field, then the work done in moving the object along the line segment from 1, 1, 1 to DDD is k divided by radical 3 times 1 minus 1 over d. As d goes to infinity, work goes to k over radical 3, which implies that the work required to escape Earth's gravitational field is finite, which makes flight possible. Take care, and I'll see you in part 3.